So, welcome to Introduction to Manufacturing. Today we'll be covering how we solidify materials. And in these cases, the starting work material will be either a liquid or it could be highly plastic. And then what we're trying to do is solidify the part so we can get the final product. So that's really what we're after here in this case. So what we want to discuss today is the casting of metal. So that's the very first one here. And that's what today's lecture is about, is the fundamentals of metal casting. And so what is casting is the process in which you take a metal that's molten and then it flows by gravity or some other force, right? And you force it into a mold. It could be again through gravity or an external force, and then it will fill that cavity, and then you're going to solidify the metal that's molten into the shape of the mold cavity. And so in essence, by solidifying that shape that was fluid, we call that casting process. And that term casting also applies to the part made in that process. And the three steps are fairly simple, or they seem simple. Melt the metal, pour it in the mold, and then let it cool off. So what is the ability and capabilities of casting? You can create very complex part geometries. That's why casting is used actually quite a bit. You can create a lot of external, internal shapes, and some casting processes are net shape, while other ones are near net shape. Meaning, in other words, there's very little waste produced. Sometimes casting can create a rough surface and they do a secondary machining process to try to smoothen the surfaces, but for the most part, that is not done. It can produce very large parts, that's another advantage, and some casting methods are suited to mass productions. Now, there are disadvantages of casting, and there are reasons why we don't use them widespread, although they're amazing, is that there's limitations on the mechanical properties you can achieve. Another one is there's poor dimensional accuracy. And like I said before, the surface finish can be a problem for some of the processes. Safety hazards can be an issue due to hot molten metal, but that has been reduced with additional safety protocols. And there's environmental problems. One of the things I want to mention here is that the mechanical properties can be a big issue. The kinds of defects you can have in casting can also be an initiation point for failure. And that is something that we really try to pay attention to. There's parts, many parts are made by casting. That includes like engine blocks in a automotive vehicle, wood burning stoves, machining frames, railway wheels, pipes, church bells. A lot of pump housings can be made this way. Valves, for example. You can also make small parts made of casting. For example, dental crowns, jewelry, small statues, frying pans. So yes, there's a lot of different kinds of applications, and it varies also about the types of materials used. It could be ferrous or non-ferrous. So casting is actually used in aerospace systems quite a bit. Aircraft, launch vehicles, spacecraft. So it's not just mechanical, but also aerospace applications. So looking at the overview of the casting technology, casting is usually performed in a foundry is a factory equipped for making molds, melting and handling molten metal, and then performing the casting process and cleaning the finished casting. So anytime I say foundry, it involves the process of melting, it involves the casting process, and involves the finishing casting process. And the workers that perform the work are called foundrymen, although that terminology has been favored for gendered unbiased, but I call it foundry work folks, but we try to remove the word men. The mold in casting, so when I look at that, that typically is what contains the cavity, whose geometry determines the part shape. The actual shape of the cavity must be slightly oversized to allow for the shrinking process. So in other words, you want to make that cavity a little bit larger so that when you have shrinking because of the coefficient of thermal expansion, you're going to have some amount of shrinking during the solidification cooling process. So you want the actual size to be the one you want, and to do that, you want to basically have the shape of the cavity must slightly oversized. Now, The mold material also matters. Typically, it could be sand, plaster, ceramic, or metal. And here's an example of an open mold versus a closed mold. There's two forms here. So the first one is open mold on the left side. It's a simpler container in the shape of the desired shape. On the right side, you can see that here's your cast metal in the cavity. And in this case, it's a closed mold. And in this case, you can actually create complex parts. And it does require like a gating system leading into the cavity. We call that the passageway. So the molding casting is one where you can have a cavity whose geometry determines the part shape. And I discussed that. And you can see here the shape for each of them. There's two categories for casting processes. Expendable mold processes. The mold must be destroyed to remove the casting in this case. So you have to get rid of it. That type is going to be typically sand, plaster, or similar material. But if you have a permanent mold, it's going to be metal. It's used less commonly because it's expensive. But this one allows you to use it over and over. Here you have the sand casting mold system. Here's your mold. Here's your gating system that we talked about. Here's your riser. It's not showing up, but that's your riser. And it was shown here, riser here. Here's your pouring cup. So here's where you're pouring the material. And then it goes into this area here that allows it to then form the part. So but what about forming the mold cavity? So the mold cavity in this case, because what I'm talking about here is sand casting, right? So we want to focus on that. It's formed by packing the sand around the pattern. So you're really packing the sand in there, which has the shape of the part. And then when the pattern is removed, the remaining cavity of the packed sand will have the desired shape of the cast part. Now, the pattern that's usually used is oversized, like I discussed before, so that the part can shrink, allow it to shrink, and actually achieve the targeted dimensional geometry that we want. Now, the sand for the mold is typically moist and contains a binder to maintain the shape. Now, there are cases where you could use a core in the mold cavity. And so the mold cavity provides external surfaces of the cast part. But in addition, a casting may have internal surfaces. So if you want to have internal surfaces, you can use a core like this one here. This is the core right here, the gray here. And it's placed inside the mold cavity to define the interior geometry. So that's why that core is used. Now, the core can generally be made of sand too. No problem. Now, the riser in this case is a reservoir. And what do we have that for? The reservoir is there to compensate for the shrinkage of the part during the solidification process. So what's going on here is you have the flow of the molten metal going through in liquid form, but this extra reservoir basically has extra material to ensure that we're compensating for the shrinkage that will occur. Now the riser has to be designed to freeze. So in this freeze is basically under quotes so that you can have the main casting do its main function. Now pouring the metal, molten metal is very important. The metal must flow into all regions of the mold. And so it's important that it happens before it solidifies. So the factors that describe the success of pouring that flow in is what temperature I'm pouring in, the rate of pouring in, and the turbulence. So there's an important parameter called the Treverner's rule. And that talks about the solidification time. So solidification typically takes time. The total solidification time is the time required for casting to solidify after pour. So basically what time lapse is required for the casting to solidify after you pour it. And so that solidification time, which I'm going to call TTS, really depends on the shape and size of the casting by this relationship that you see here. Now Cn here depends on the mole constant. It's an experimental value. V is the volume of the casting. A is the surface area of the casting, while N, the exponent, is typically 2. So if you have this information, I can tell you how long it's going to take for something to solidify after you pour it. So looking at the Treverner's rule, what it tells us is that the casting with higher volume to surface area, so if the volume here is greater than the surface area, right, that's going to take longer to cool and to solidify. And it's going to be slower than one that had a lower ratio. So to feed the main cavity, this time to solidify for the riser must be greater than the time to solidify for the main casting. You want to make sure you're not solidifying this too quickly. You want the time to solidify for this to be greater than for this. Otherwise, you'll have an issue. So again, I'll repeat one more time. The time to solidify for this riser here, whatever fluid is here, must be greater than this for this to work. Now, since the mole constants of the riser and casting will be similar, the design of the riser to have a large volume to area ratio needs to be designed in such a manner that we can minimize the effects of shrinkage. So we want to make sure that the way we design this riser and the way we define the casting, that we're able to minimize the effects of shrinkage through this process. And that's what this is a very important parameter to be able to calculate. Now let's look at the shrinkage in the solidification process and cooling. So when I look at this, here is the immediate level after I pour it, and that's your molten metal. And then here is a reduction level due to the liquid contraction. So basically, once things start to solidify, you're going to have some amount of contraction. You can see here a change in level, but also a change in moving away from the mold. And then the reduction in the height due to the solidification process, you can see that here. But if you were to have molten metal and some amount of solid metal that starts to solidify, so the darker region is solid metal that start to solidify, you will have then areas that need to continue to solidify. And that can cause some areas where you have voids or cavities that form. And that could be a problem. So let's look at the step by step. Number 0, I start to level the molten metal after pour. Number 2, there will be a reduction in level caused by the liquid contraction. You can see that there. And now these are all exaggerated, obviously, to be able to show the effects. And then you have a reduction in height and formation of the shrinkage cavity caused by the solidification shrinkage. And 3, you have further reduction in height, a lot more, and then away from the walls due to the thermal contraction. And in some cases, you could create cavities, which could be a problem. So there's something called shrinkage allowance as a consequence. So pattern makers do account for this shrinkage and the thermal contraction by making the mold cavity oversized. The amount by which you make that mold oversized needs to be calculated. We call that the final casting size is also called the pattern shrinkage allowance. And the casting dimensions are expressed linearly, so the allowances can be applied accordingly. Now, looking at directional solidification, basically to minimize the damaging effects of shrinkage, it is desirable for the regions of the casting most distance from the liquid metal supply, so in this case we're looking at here, to freeze first, and for solidification process from these remote regions towards the riser. So in other words, I want to have molten metal continually available from these risers to prevent shrinkage voids. I want to prevent this. I want to prevent these voids and these voids. How do I make sure of that? I need to make sure that the molten metal is in these risers are continuously available and they're injecting more and more to fill out any of those voids. And so the term that you may hear out there in the casting process of directional solidification really describes this aspect of freezing and methods by which we're controlling them. So achieving solidification, directional solidification, that is achieved by using the Churano's rule to design the casting itself. You're going to orient the mold in a way that the riser system fits it properly. You want to locate section of the casting with lower volume to surface area ratios away from the risers. So you're focusing away from the risers. These is where the issues could be. So freezing occurs first in those regions, and the liquid metal continues to supply the rest of the casting, which is remaining open. And you have a term called chills, typically in these processes, which is internal or external heat sinks that cause rapid freezing in certain regions of the casting. So here's an example of external chill. So here, the external chill encourages rapid freezing of the molten metal in the thin section of the casting. And then here in B, what you see is a likely result if I didn't have external chills. So this external chill is really focusing in areas where I could have this issue, and that allows it so that you don't have these voids. So metal casting processes is what the next lecture is about. So we're gonna pause here and then we'll continue in the following lectures to discuss this metal casting processes. Thank you for your attention, but the lecture today ends here. Okay, we ended the particular section for today. So today's lecture will be covering metal casting processes. So it's the second part of the lecture. We've previously covered metal casting processes, but today we're going to go a layer deeper. So there's two categories that we talked about, the expendable mold processes and the permanent mold processes. Both of them had advantages and disadvantages, and we talked about those before. Permanent processes, mold processes, really allow you to get high production rates, but the disadvantage is that the geometries can be limited in many cases, right? Now, when I go deeper into the expendable mold casting processes, sand casting is the one that's used a lot in industry. We talked about it. And is most of the casting processes, a lot of it constitute the majority of the total casting process parts that are produced in the world. You can produce many quantities, up to a million of them, and the castings can be very small to very large. On the bottom right, what you see is an industrial pump that was manufactured using a sand casting process. Another thing that we talked about before was that steps in the sand casting process require pouring the molten metal into the sand mold. You allow the metal to solidify, and then you have to break the mold from the casting that you have in there. You then usually do an inspection. Let me talk a little bit more about inspection. So with casting, typically is a good idea that after you cast the part, you do something called a computer tomography, CT scanning. Micro CT technology can detect voids in the part and can give you a good feel for how good the quality of the part is. That's one approach that has been used in the industry. Other approaches that people have used for inspections is called an X-ray can also find defects within the casting that cannot be otherwise found. So very good two approaches are used. And the last aspect is that heat treating cast parts can really improve the properties of the part by really allowing better mechanical properties to be achieved. Here, what you see is a sand casting procedures that describe verbally. So we did cover this previously, but the thing I want to talk about is that this process does require a cleaning operation, and not just the inspections need to be done, but the cleaning operation can be significant. The pattern materials that can be used can go from wood, metal, or plastic. Any of these materials have been used. Metal is more expensive typically, but it will last longer in general. And the pattern usually is a little bit larger to allow for some shrinkage to occur. So yeah, I covered a lot of this. We talked about the core being used to be able to create features internal to the casting part. And a lot of times, the way that you will support a mold cavity like that during the pouring, that's called chaplets. So that's something you may hear in industry. But again, it is in the details, in the weeds, just more for your knowledge in general. Because really what I want to get out of you from this course is the following. I want you to learn the casting process achieves a net shape design with very little waste, number one. Number two, there are going to be defects that occur in these processes. Three, it's very difficult to maintain a dimensional stability that is appropriate. So all these things is what I want you to keep in mind, and also the importance of inspection and cleaning. Here is an example of a chaplet. You can see it here. These things are holding that core in there, so it can be held in place. And then you can do castings of internal cavity as a consequence. There's another concept called buoyancy. So when you pour this molten metal, there's a buoyancy component where the molten metal tends to displace the core. And that's a very well-known issue with these types of manufacturing. The problem with buoyancy is a buoyancy, because of that effect, it can cause a lot of defects in the part. And there's a calculation that can be done, and the calculation is a force that is equal to the weight of the displaced liquid less the weight of the core itself. So that's the formula right here that's typically used. The idea is to be able to reduce the effects of buoyancy as much as possible. So what are the desirable mold properties we're seeking? What is ideal for us? We're looking for something that has great strength so it can maintain the shape during the manufacturing process. You also want something that will resist erosion. I think permeability is so important because it will allow the hot air to be able to go through the material instead of just conduction. The hot air can go through all the cavities of the mold and reach the actual molten metal effectively. And so in sand, you do get that effect, which is very nice. Thermal stability is another thing that we're looking for because we want to be able to resist cracking. The thing you don't want is that when something touches your mold, it now produces stresses onto the mold that crack it. So thermal stability is so important. Collapsibility. You don't want your mold to collapse. So the ability of allowing the casting part to shrink without causing the casting to crack is instrumental. Why? If the casting cracks, now that imprint will be on your part. And you don't want that situation. You also are looking at the bottom here when it comes to using that cast again. And so that's another one that can be considered that should be thought about. We did talk about foundry sands. The main point here is that silica can be used with other minerals in that process. It has great refractory properties. Small grain size allows a very nice surface finish. That grain size is very important. If you can maintain those grain sizes very small, then your surface finish is going to be very nice. Now, if your grain sizes for this effort here is too large, you're going to have a lot of surface roughness. And surface roughness is a potential issue for fatigue initiation and cracking. I want to mention that a lot of things I say are not in the chart. So I hope that the audience is taking notes, right? These are very important things I'm saying. So this part that could have surface roughness, any surface roughness can become a stress concentrator. So when this part goes under cycle loading conditions, it can now initiate a crack prematurely in the part and then propagate. And then combine that with potential defects within the part, and things can become much of an issue. Now, the other thing is that large grain size is more permeable, and it allows the gases to skid more easily during the pouring process. So there's multiple things going on here. Irregular grain shapes strengthen the molds due to the interlocking compared to round grains. So having irregular grains in the sand material is actually kind of beneficial here. Having everything uniform makes everything move around much easier. The disadvantage is that interlocking does reduce the amount of permeability, and that is a disadvantage. You do like permeability when it comes to this casting processes. There's also something called binders with foundry sands, and the idea here is that you have a mix of sand, water, and clay. So that is kind of the composition typically. You can use bonding agents like phenolic resins, sodium, silicates, and phosphates. And you can also add additives to this process. There are other expendable mold process. The book goes into extensive detail in the introduction to manufacturing here, where they talk about shell molding, vacuum molding, polyester processes, investment casting, and then plaster molding. So those are the ones that you will see. And he'll provide some examples of that. So for you here, as an example, you see shell molding. This is a casting process where you have a thin shell. So here you have the sand with a resin binder. Here you have the heated pattern. That's the one we're talking about here. And then you have your heated pattern here, the heated load applied here. And then these are your box, for example. And now I'm going to push this material onto this heated pattern. And then that's going to create a little shell. And then when you heat it up in the oven, that shell material can now be extracted. So yeah, those are some examples of shell molding that you may see. What are some examples of that? Like a dumbbell can be manufactured that way, as an example. What is the advantage and disadvantage of this approach? The advantage is that you get very nice smooth cavity surfaces, good dimensional accuracy because of a very limited amount of machining required. So very little waste from that perspective. The mold collapsibility is not an issue. And you can mechanize this for doing a lot of them at once. So you can do a lot of things here. But the problem with this approach is very expensive. And you can, like, if you want to do a small quantity of it, maybe you may as well just look for a different manufacturing technique.
because of the expense associated with this approach. Vacuum molding, what it does, it uses a sand mold that's held together by vacuum pressure. So it's not held by a chemical binder, but it is by vacuum pressure. And the term vacuum, what it refers to here is a mold making rather than the casting operation itself. So here's your pattern, and you pull the vacuum in here, and now you can then extract the mold to then create your part. So it's using vacuum to pull the material into that mold, and then when everything solidifies, you pull the mold out and you achieve very nice parts. Now the problem here, the benefit here with vacuum pressure, the benefit there is a pressure is going to try to compress the material to then remove the voids that are internally in there. Again, this is not in the notes, but I'm explaining to you from experience. So there's a benefit there of vacuum pressure because you can try to extract those voids out of the process. The advantage and disadvantage here is that it's easy to recover the sand since there's no binders associated with them. The sand does not require mechanical reconditioning because of the binder issue. You have no binders. And since no water is mixed with sand, any moisture, because I told you before that moisture can be a problem in these casting processes. I don't have moisture issues in this process. There's a benefit here. Now, the bad issues with this approach is that it's very slow and you cannot really adapt that for mass production. That's the disadvantage there. You also have something called expanded polystyrene process. Other names that people have used for these is called the lost foam process, lost pattern process, evaporative foam process, and the full mold process. If you hear any of these names, that's the same thing as the top there. So what is this approach is using a mold of sand that's packed around a polystyrene foam pattern. And that foam will vaporize when the molten metal is poured into the mold. So here you have, say, the shape of what you want to mold. You spray it with that foam pattern. You put it within the sand pattern. You pack the sand around it, is what I'm intending to say. And then when I pour the molten metal, it displaces and vaporizes the foam pattern, which is why it's called process, because you're losing foam out of the process. And so this approach has advantages. And you may say, well, why I'm doing that? Why not do that? Well, the advantage is that the pattern doesn't need to be removed from the mold. That's one advantage. Two, it really expedites the mold making process. It's faster because if you have two mold halves, they don't have to be in a conventional mold that we talked about before. What is the disadvantage? If you want a new pattern, you have to create that every time. Also, it can be expensive. So that's something to keep in mind. Because making patterns is costly. So that process can be expensive. Another one that I think you may have heard, and I don't know if you've heard it, but it's called investment casting. So now you have a wax pattern now that you're using, and this wax pattern is typically coated with a refractory metal. Hopefully you know what a refractory metal is. We talked about that. Refractory materials are materials that can take high temperatures. And these refractory materials, you're coating the wax, to make the mold, after which the wax is then melted away from the pouring metal that you're using. So here is an example of a wax pattern. Here's your wax sprue here, and then you start rotating this. Let's see if I have a picture of the rest of it. Here's your wax now being poured out, right? And as I pour out the wax with the heat applied, you can start to see now that my mold has formed. You can see that. So think of investment casting as a process where I'm now losing wax instead of losing foam. So very similar approach, but now I'm losing wax. Here is a great example of something that can be made with a lost wax process. Here is a compressor stator with 108 separate airfoils. And they were able to make this with very high quality using this approach called investment casting. So I really encourage you to look at this approach to make very complex parts very successfully, but it has advantages and disadvantages. The disadvantages is that it is costly, very expensive. And the other thing is there's a lot of steps that are required to make that happen. Now, the advantage is you can make a lot of complex parts, like I said, with a lot of intricate features, great dimensional control. That's why you can make something like that with airfoils that are that small. Wax can also be recovered and you can reuse that. So, for example, here you can see that I have my wax pattern. I coat that pattern with refractory metal, and then I have my molten metal, and you can see here's when I'm coating it. I'm coating to this material, and then I put it upside down like this, and I can rotate it to then remove the molten metal, right? I mean, re-explaining it in case it was not clear. But as you do that, the wax is coming out too, right? The wax is coming out too. And so that process is going to leave, an impression like this, right? And so, yeah, so just like the one for polystyrene, here you're losing foam, here you're losing wax. That's why both had the word lost. But yeah, additional machining is not usually required. You get a lot of benefit here in terms of the net shape, and the wax can be reused, which is amazing. The permanent mold casting process, just like for expendable, you have to create a new mold every time. With permanent mold casting, the mold can be used many times. And the three processes I've seen in industry are a basic kind, the die casting, and centrifugal casting. So those three are very common. Let me cover each of them for you. You have the basic kind here. Let me see if I have a picture. Yeah, I have a picture, but I'll kind of cover the big picture here. You use a metal mold. It will have typically two sections. They're designed for opening and closing very easily, for example. These molds are used for casting lower melting point alloys. And so you'll basically, these are typically made of steel or cast iron as a consequence. And most of these molds used for casting steels must be made of refractory materials because of the very high melting, very high pouring temperatures you're dealing with. So for that reason, it's very important to make sure that we have those characteristics for that mold locked in. So here, what you see in step number one is that the mold is getting preheated. So you're preheating this and coating this. If you have cores, you're gonna have to use chaplets again to keep the core in place. Remember the core in the exam, if I asked you what are core used for, they're used to be able to create internal features within the cast part, right? So very important. At this point, realize what we're doing here, and that's what's called basic. This hydraulic cylinder, what it does, it opens and closes the mold. But when you're done with this process, you're ready to close the mold, and you're gonna have this cavity here. And next, what you do, you pour the molten metal. Here you can see the core is in place. The chaplets are basically the mold themselves, keeping it in place. But when I push that through the molten metal, it will solidify. And then once it solidifies, you can then take the hydraulic cylinder and pull it apart. So what is the advantage of this? You get good dimensional control, more rapid solidification, but the limitations is you're limited to metals with lower melting point. And you can make only simple part geometries compared to the other ones that you saw, and the molds are very expensive. And so what I'm hoping you can do, and maybe that's a good way to prepare yourselves, is to create a big table. The first column has a type of casting process, and there's two categories there, right? There is the one that's expendable and the one that's reusable. An expendable one could be the casting one that we talked about, the lost wax, the lost foam, all the different ones, right? And then for the expendable, there's the basic one, there's a die casting that we'll be talking about, the centrifugal casting one that we'll be talking about soon. And it would be very nice if you can take that and create a second column. And the second column says how it works, right? How that each of them work. Very simple, with very simple paragraphs. The third column can be what's the advantage of each of them. And the fourth column can be what's the disadvantage. And if you were to do that today, by the end of this lecture, right, tonight, for example, maybe you solved one of the questions in what's coming, right? So maybe I'm giving you a clue there, but listen, the material is here. All you have to do is organize it. And what I'm trying to do is push you to kind of compare these in your head. Not in your head only, but looking at, okay, I want to make this part, right? I want to make this part. Without seeing what the title of this chart is, you can quickly say, I want to make this. I think investment casting will be better because I can do this. I can get dimensional control that's very nice. I can get great complexity. Are you following what I'm trying to say here? Yeah. So very important that we can do that. We can learn, right? We can learn the processes so that when you go to industry and you want to achieve a particular design, you can say, okay, for this design, this is the kind of manufacturing I want, right? Part of being an engineer is not only to design, but understand whether the part, you don't want to be a designer that makes a design in a CAD software, and then you don't know how you can even make it. That's an incomplete engineer, because that means that maybe the part is not even manufacturable. That could be a possibility. You made something in the CAD software that cannot be even made or manufactured. Or you want to achieve a particular dimensional tolerance and you chose a wrong manufacturing casting process, right? All those things we need to keep in mind as we work through this process. Die molding is one where you inject the mold cavity in there with high pressure applied. And that pressure, you will maintain it throughout the whole solidification process. Then the idea there is you take the mold, you open it, and now you have the part. And that's what this is kind of called die. That's where that's coming from. Because the molds in this casting operation themselves are called dies, and that's what that's called, die casting. But the idea is here to use the high pressure to force a metal in the cavity. And by doing that, you're actually trying to remove voids also through that process. And that's actually very different from the other ones we looked at, right? There are two kinds you will see in the street. The two, one is the hot chamber machine and the cold chamber machine. They're kind of funny names, actually, but both of them have been used with a lot of success. Let's look at the hot chamber die casting. Here you have your chamber, here you have your pot, here you have your plunger, and here you have your fixed die half, one of the halves. Here you have the other half. This to eject the dies from each other. This is a cavity we're interested in, right? And so what you're trying to do, you're trying to close this die and then apply pressure to push that through this nozzle into this cavity. So that's what's gonna cause it to go in there. Okay, the metal is then melted in the container, and then here now it's in here, so it's melted in the container, and a piston will inject now the molten material successfully. So what is the advantage of this approach? High production rates. You can make a lot of parts per hour. And that's pretty amazing. Applications are not just limited to low melting point temperatures, but you can actually look at higher temperature applications. You can cast stuff like zinc, tin, lead, and magnesium. So that's very nice. So yeah, that's the thing to keep in mind. I don't know if you know, but zinc, tin, lead, and magnesium, they have very low melting points. So that's why this approach is very nice for that. Cold casting chamber die is very similar because I'm not using as much heat anymore. The molten metal is poured into the unheated chamber, while here I was pouring it into a heated chamber. So that's the difference. One is hot because it's a hot chamber. Obviously, the other one is cold because it's poured into something that's not a hot chamber. So here, you close the casting and you inject the molten metal by applying a force to this plunger here. It pushes that into, it pushes the molten metal into here, which is very nice because it removes the voids again. So it forces the metal in there into the die. And then the issue here is that the production is not as fast as the hot chamber. The problem is you can only really do certain metals. And those certain metals here is aluminum, brass, and magnesium alloys. Cannot do everything. So are you starting to see the light? Like if I told you for a particular situation, I want to be able to do casting for zinc. True or false? Should I use a cold chamber? The answer should be false. If I want to do zinc, I want to use a hot chamber, right? If I say I want to do high production, okay, this works for zinc. So the idea here is that you understand what you want to achieve at the end. Do I want to do a mass production? What metal I want to work with? I really like what about a lot of you said. Very good answers today when I said, what are we trying to teach in this manufacturing course? I really like what you said about, it tells you about design options. It tells you about design limitations. It tells you about manufacturing options. It tells you about certain processes can be lend themselves to more quality issues. So understanding that in the context of casting, I think is extremely important. And it'll make you a superb engineer if you can get there. Now let's talk about the molds themselves when it comes to the die casting. These tend to be usually made of steel, typically, or another term that I don't know if you've ever heard, but it's called miraging, which is martensite. plus aging steel. Tungsten is another one because tungsten has good refractory properties and they're used to die cast steel and cast iron because, as you know, steel and iron require high melting temperatures. So you need something even higher in terms of capability, temperature capability. And then the ejector pins I talked about before, but those are required to be able to remove the part from the die. Without those ejector pins, you can't really get the part out. And that's why it's so important that you spray. I don't know if it's written here, but yeah, here is to spray the surfaces. Spray the surfaces with lubricant because what you don't want the part to get stuck. That's the least thing you want. You don't want to make a part and then you can take the die apart. So lubricants is extremely important in these processes. The advantage of die casting, like every single one of them, what I like about the chart is that every single one of them tells you what's the advantage, what's the disadvantage. And the idea here is that you get really good surface finish is one of the things I like about this process here. And the other ones, you can make very thin components that are not possible any other way. Rapid cooling. And then the other one is economical for large production quantities. Again, the disadvantage is limited to metals with low melting points, and the part geometry must allow removal from the die. Now let's look at centrifugal casting. And I think you kind of get where I'm going with the centrifugal casting without me even talking about it. You can start imagining, right? Can you start imagining what centrifugal casting could look like without ever looking at it for the first time? I think you can get there with me. There, what you're doing is you're using a mold, but that mold is rotating very fast. And what that does, it takes the molten metal and it pushes it out, right? Outwards towards the die cavity. Now, there's three groups that people use: the true centrifugal, the semi-centrifugal, and the centrifuge casting. So those are the three that you may hear. Let me go through a true centrifugal casting. So the molten metal in this case is poured into this rotating mold. This obviously a side view. And this piece here, this piece right here, is this one right here, okay? And then these pieces here are the ones here. And what you're trying to do, you're trying to rotate at high speeds, and that's going to cause these centrifugal forces are going to cause this molten metal to be distributed to the outwardly in the inner, you can see this mold, this inner surface of that mold. And that's very nice because you can make a lot of parts like pipes, tubing, bushings, rings, and the outside shape can be amazing. It can be a hexagon. I don't care. It can be some other shape. As long as you can actually rotate at high speeds, you can get the molten metal to go out there, right, to the inner surface of that mold and start getting a part that you want. Now, semi-centrifugal casting is a little bit different. In this case, you're creating solid castings, not tubular. Like here, you're going to have, in the center, you're going to have empty space. Here, in this case, it's very similar where you pour the material here. You're going to have the casting material around it. And what you're doing here is you're pushing the material in and then rotating that at very high speeds. And now you have a solid part instead now. So, right, that's the difference between this and that. So here, I'll say you can make wheels and pulleys, for example, with this process. And it tends to be very powerful technique. Centrifuge casting, also a very good approach. Let's look at the figure here at the bottom. Here, what you have is that you can start making parts that go into complex shapes on the outward edges. You can see that there. In this case, you have a rotating table here at the bottom. Here's your material that forms a casting material. Yeah, so this is a great approach as well. You can do a lot of things with that. Okay. So additional steps after solidification. I already covered it, but I'll kind of repeat quickly. Trimming, removing the core, surface cleaning. I already talked about all of that. Inspection, if you need to repair, we can do that. And then heat treatment. And repair always goes after inspection because if you find a problem, perhaps there's something you can do. But those are the steps we talked about. The casting quality, we talked about those already. There's numerous opportunities for castings to go wrong. As you see, these processes look very stochastic. They don't look very deterministic, like CNC machine where you know exactly how you're cutting things. There is a level of uncertainty. These things will shrink. These things could be uneven. You could have uneven heating causing voids internally. We've already talked about this, but the defects that can occur can be those very specific to casting processes or more general to any process. So here's an example. Let me give you through some examples and their names because I think it's very important to learn this. The first general defect you may see is called the misrun. In this case, the casting has solidified before even completed filling out the whole mold. And the questions will be asked from you to tell me what the defects types are and what they look like. So again, one more time, misrun is very easy. Misrun is that you are not able to fill the cavity, period. And so you have a part that didn't quite get there. A cold shut is a situation that I described before, where you have portions of metal flow that they flow together, but there's a lack of fusion because you have a premature situation where things got cooled down at different times. The defects that you get out of this is cold shut, is what you may hear in industry. Is a lack of fusion of the metals. There's another one that's different. This is called shut and this is called shot, right? So two different kinds. Here you have metal splatters during the pouring and solid globules. Basically, you have metal splatters that kind of start suspending within the metal. And that can become entrapped in the casting. Shrinkage cavity, I think we talked about that too quite a bit, but I'll repeat it one more time. You get a depression in the surface due to an internal void caused by solidification shrinkage. So that can be an issue as well. So you mentioned it. Thank you for doing that at the beginning of class. Sand blow is another kind where a gas can form. So you get like a little bubble there. And the gas cavity can be caused by the release of mold gases. So really what's going on here is that the mold itself is releasing gases, is causing a defect right on the edge. Pinholes is another one. Again, now you have small gas cavities that's slightly below the surface of the casting. And why is that so dangerous? It is dangerous because you may not see it with your superficially. It's going to look great, but just below the surface, they're ready to be a problem. And you can only find this through a non-destructive evaluation. And that's why it's so important to conduct those operations. The other one is called penetration, where the molten metal now starts basically permeating into the casting itself, the molding itself, the mold material. So when the material starts to wick into the molten material starts to wick into the mold, you start to get these imperfections where we call it penetrations. And that is not good because now that outside surface is going to have a mixture of that sand mixing with metal. And when you solidify it, you don't know quite what you have at the surface. It's going to be a mixture of materials, and that is not a good thing.
Of course, when these defects occur, is the solution usually just to like redo the casting itself?
No, so a lot of it, like this process here, if it does a great question, thank you for that. One solution here could be that you machine it to take care of those asperities, right? Let's go to this one. One solution here is to make sure that you can do an analysis. You can characterize the distribution pinholes and then do something called a fracture analysis or strength analysis. You can also do testing to determine if these pinholes will be a problem. When it comes to sand blow, it will be very obvious on the surface. There are approaches to either sand that out is one approach, or you can use new techniques now that spray metal on that surface to kind of seal it off. Is that helpful?
Yeah.
Let's keep going. Shrinkage cavity. I can also look at that and see, okay, is that going to be a detriment to the performance of my application? If the answer is no, no problem. If it's a detriment, then I had to find a solution. One solution is to machine off, and it's going to have a little groove. If I did that, is that groove a problem? If I can't have that groove, I have to think of other solutions, such as filling that out with another approach by like a spraying metal or something. The cold shots, similar to the ones I discussed before, you have to evaluate the effects of those stress concentrations. Using finite element analysis could be one way, or testing. Cold shots are very complex issues, and they can degrade the properties quite significantly. But again, all these different kinds of issues need to be evaluated against the intended use, the performance characteristics you're seeking, and whether you can do something about it. If you can do something about it, you're going to have to rethink your manufacturing process and improve that through something we call improvement processes. You're going to implement corrective actions to improve the quality of the build by making modifications to the casting process. Here's an example of a misrun, right? In this case, something went wrong. And what went wrong is that the molten metal could not make it to the very end. What could that mean? Maybe we have to apply some amount of pressure, like some of the other ones we saw, some of the other casting processes. Another approach is, can I use this material with a little piece off? And so I'll do an analysis about that too. I don't know if I'm answering the question, but all of these techniques, doesn't matter what manufacturing technique you're talking about, each manufacturing technique is going to result in very similar outcomes. Number one, repair. Number two, use the component as is. Number three, reject. In a lot of cases, you are able to use it if you can do testing analysis or inspections that give you the confidence that the performance characteristics of that part that came from the manufacturing process is such that it's going to lead to extremely good performance. There will be no degradation in performance if you can be okay with that. There might be cases where degradation performance is acceptable. You're going to have to evaluate that as an engineer and decide whether it's worth getting too perfect. Because engineering is not about perfection. Engineering is about understanding what the function is that you're trying to achieve, what is the right level of function, and what part I'm trying to build to get there. And when I do that, that part will be defective. We know that. All these manufacturing techniques you're learning will have defects. The question is, are they rising to the level that you have to reject the part, which you don't want to do if you can help it, because it's costly, right? So let me keep going here and we'll talk more. I will talk more to you, no problem. We have the mold shift. That's a big one. If you have die casting where one side of the casting mold can shift relative to another, then you can now create a little indent or a little shift in the cast part, and that can be a problem. That could be a significant problem. So metals for casting, most commercial castings are made of alloys rather than pure metals. Very rarely you're going to use castings for gold and things like that. It is used for gold and things like that, but the majority of the commercial castings is for alloys, not for silver, copper, or cast alloys can be classified as ferrous and non-ferrous. We talked about it before. Sorry if I'm a little bit repetitive. Most important of all casting alloys tends to be cast iron because of the high temperatures that we can achieve there. That tends to be very good for casting. Yeah, so steel is another one for is a ferrous casting alloy also. The mechanical properties of steel make it an attractive engineering material, capable to create very complex geometries. And ferrous alloys like steel, the properties are very nice. There are some difficulties when it comes to casting steel. That's because the pouring temperatures are very high, and at these high temperatures, the steel can oxidize. That could be an issue. And the molten steel has very relatively low pore fluidity, so meaning that the viscosity of it is not quite there for you. So that could be one negative side of steel. Aluminum, very castable. You will see this a lot because the temperature, the melting temperature you're looking at is 660, which is relatively low. So it's easy to deal with from that perspective. Lightweight, the range of strength properties by heat can be achieved by heat treatment. Easy to machine. Like after you're done, you can do some machining. Copper alloys, that includes bronze, brass, aluminum, bronze. Good thing about copper alloys, I already talked about it before, but it's a repetition. They have great corrosion resistance. They actually look very nice. So there's a benefit to that if that's what you're going for. Good bearing qualities. Let me talk about that a little bit because it may not be clear to you. But attraction is so important when it comes to manufacturing for consumer products. There's been studies made that you can have a very robust design, but if it's not appealing to the human eye, it's very unlikely that you're going to buy it. So it's so important that not only you focus your efforts in achieving a good design, but that you work with a consumer designer that understand aesthetics, because that's part of selling something, right? There's something slick about these kinds of phones, right? Although I have the competitor right here, but there's something slick about it, right? There's something, unique about how a laptop could look like versus a iPad and things like that, right? So these are the kinds of things you want to keep in mind. I forgot to mention. I was focusing on quality and intended function, but I did want to bring attractive appearance, and I have forgotten about it. I apologize to you. Very important property, especially for consumer applications. And even goes beyond that, safety can be also very important. So yeah, you have to think about all those things. Copper alloys have great bearing properties too. And so you'll see them here in pipe fittings in homes. You will see them using marine propellers, pump components, and even jewelry. because they're a great material for corrosion resistance. Zinc alloys, very castable. You'll use it in die casting, very low melting temperature, makes it easy to, it's viscous, easy to be malleable. However, the properties of these materials, they have low creep strength. And so castings cannot be subjected to prolonged high stress environments. Now, I worked on an investigation of the Arecibo radio telescope collapse. I grew up in Puerto Rico and I worked on that particular telescope to understand why the Arecibo telescope collapsed. And I was one of the investigators for NASA. What we found was that the joints on how these cables were secured were inserted into these joints using zinc casting. And because of the Hurricane Maria and subsequent creep environments of sustained load conditions over a long period of time, it was found that the zinc started to creep over time. So slowly, the zinc was getting pulled from the socket until it gave out and it broke apart. I invite you to watch a couple of YouTube videos on how it failed. I think you'll gain a lot of knowledge on what happened there. Is a great application to understand this. Number two, I helped author a report on the investigation. So if you go to the NASA server, you can download the Arecibo Radio Telescope report to understand what caused the failure. And you'll see that we talk about low creep strength being a problem for that application. So very interesting thing, you know, something dear to my heart because I grew up there. And Arecibo Radio Telescope is an icon for Puerto Ricans. So yeah, I felt very connected to that project as an investigator. Product design considerations, geometric simplicity. Casting can be used to produce complex parts. And so it can simplify the processes, and that's why people love it. You can avoid unnecessary complexities, simplifies the mold making. You can also reduce the need for cores, I'm sorry. And you can improve the strength of the casting by using heat treatment. There are things that we can talk about on the considerations for the design using casting processes. The one is sharp corners and angles should be avoided because castings have difficulty achieving those very well. And since they're the sources of stress concentrations, they may cause hot tearing and cracking. So yeah, that's why it's so important to stay away from them if you can. Keep those fillets in there. Try to have nice, generous fillets that will reduce the stress concentration if you were to use castings. Another type of product design considerations is draft guidelines. So an expendable mold casting, use draft facilities removal of the pattern mold. Typically, the draft we're looking there for is 1 degree. In permanent mold casting, you're looking at 2 to 3 degrees. And then you may want to look at similar tapers to allow the solid cores to be used. Other things I want to talk about is you can do very minor changes in the part design to reduce coring. Because using cores, remember we talked about cores and chaplets? Using cores can be very challenging. So if there's a way to by the way, if you don't know what draft means, I apologize, I should have explained it. That's typically covered in a CAD class. So I don't know if that was covered in your classes, but draft is this angle here that we're talking about. So having some amount of degrees of angles is very helpful. So I apologize for not explaining that well. But you can see here that I needed a core, but if there's a way of not having to have that, that's beneficial. Machining allowances, another product design considerations. Almost all casting must be machined to be able to achieve the dimensional tolerances you want. And we call that, the additional material, we call it machine allowance. So basically you're making it slightly larger so you can then machine it nicely. And also you can take care of these kinds of defects. Like if I were to have this defect, if I have oversized it a little bit, I can now machine that off, right? So there's some benefits. These are things you want to think about that are so important. Typical machine allowances for these sand castings can be between 1.5 to 3 millimeters. And if you like British units, a quarter of an inch. And with that said, it's a pleasure for me to be able to teach this course because it's exciting. It's an exciting course, right? The manufacturing processes is what allows us to be able to deliver to the community. You can design all day long and it stays in a computer, but if you can't manufacture something, it stays in a computer. And that's why it's so important that as engineers, we learn about the manufacturing processes. We learn about the different options that exist so that when you go into your design process, you account for that ahead of time and you understand what are the limitations, What are the different options that I have? And those are the things that we're trying to get across with these lectures. So hopefully you learned something new here. With that said, thank you for your time, and I'll be here to take any questions.